Now we are going to discuss about the base data available to map Mercury, and we will also have an overview of geological maps available on Mercury. And yes, this is just to give an overview of Mercury mapping also to those students that won't be with us this afternoon for the practical lessons. So, okay, how do we map Mercury? The Messenger mission provided a wealth of data sets, and the main data sets that we use to map Mercury consist in base map covering the entire planet at an average resolution of 166 meters per pixel. We also have other base maps coming from the past mission Mariner 10, for example, like this one. Here we have a mosaic between the past Mariner 10 mission mosaic and the flyby of first flybys of Messenger. This is a 500 meters per pixel mosaic, and all base maps are useful because they all provide different illumination conditions and different incidence angles. So resolution is not always the only value we care of. We also have color mosaics, as you have seen so far, and DTMs, of course. We have both DTMs produced via laser altimeter data. Unfortunately, the laser altimeter data only cover the northern hemisphere of Mercury, where we reach a maximum of 500 meters resolution. The resolution is a bit higher to the North Pole, where the best data of the laser altimeter are present. And to map Mercury globally, we mainly use the stereo DTM by the USGS, which is done by using several MDIS images in stereo images. So the best place where to explore this data and also download them is the Mercury Messenger Quick Map that we saw before. And before going on, I would like to go again in this in the Quick Map to show you the say the data sets more in detail. So this is the Quick Map, and in the Quick Map you can turn on location overlays to see the main nomenclature of the planets. But what we care about now are the global mosaics covering the planet. What you are seeing here is the moderate incidence angle map, which is also called BDR, Base Map Data Record. And this mosaic was built to provide a moderate incidence angle almost everywhere. The moderate incidence angle help us understanding surface features, especially the morphology. As you can see, there are still areas where Messenger could not provide moderate incidence angle pictures. So in this case, the mosaic is not so continuous. In any case, this mosaic is composed of moderate incidence angle images, but that sometimes may have opposite incidence angles because they gave the preference to similar incidence angles regardless of the direction of the light. So you may see sometimes some craters show an illumination from east, like in this case, while, sorry, are you seeing my screen? Yeah.
Yep.
Are you seeing the Quick Map?
Yeah.
Okay, great. So in this case, you can see there is a crater here that shows an illumination direction from east, while on this other side, the illumination direction comes from west. So the mosaic looks pretty uniform here, but there are opposite incidence angles here and there. So the messenger team also provided other kinds of base maps that provide more uniform sun direction. These are the west illumination map, where higher incidence angles are favored, but however, not all the planet was mapped with a west illumination condition. So it's not as uniform as the modern incidence angle base map. However, you have a uniform illumination from west everywhere. And the same happens for the east illumination map. Again, the base map is not so uniform as incidence angles, but you have a uniform sun direction. So the same area can be studied in many ways by using east illumination, west illumination, or a general moderate incidence angle that we use both frames from east and from west. We also have low incidence angle base maps. And you can see how the landscape changes, because in here, it seems we are looking at a very smooth surface. But from, for example, the east illumination base map, actually, it is not so smooth. It is very cratered, because this the contrast between high incidence angles and low incidence angles is very high in this case. But this low incidence angle base map is still very useful, because sometimes it enhances some structures which are oriented in an east-west direction, which are not visible in other base maps. So if, for example, we take the east illumination base map, we can see here that the east-west structure is totally disappeared. And also in the west illumination base map, the east-west structure here totally disappeared. So the low incidence angle base map doesn't enhance the morphology of the planet, but however, it enhances these structures that are mostly east-west, which is the common illumination direction on Mercury. So it's very difficult to get, let's say, shadows toward the north or the south. And the low incidence angle base maps also enhances albedo regions. So for example, in here we can see there are some dark terrains. Here are other dark terrains, light terrains, which are not visible with the moderate incidence angle base maps. So when mapping Mercury, it is very important that we use all these base maps. And we also have the color base maps, which are very, very similar to the low incidence angle base map. However, they also provide colors because they are multi-band rasters with 3 different bands in the red, green, and blue channels. So since they need different bands, these base maps also offer a lower resolution, because not all areas of Mercury were mapped with different bands. So there are several color base maps. For example, the North Polar region is also covered by a 5 color base maps, where you can choose between 5 bands. And then there is the famous enhanced color base map, which is basically the result of a principal component analysis of all available bands. Okay, so all these data sets are useful to study Mercury. And we have also the terrain elevation, of course. And we have the USGS DTM is the only one that covers Mercury for the whole surface. The whole surface is covered just by this DTM, which was obtained by stereo imaging. Then we have very high detailed DTMs. These are still stereo imaging DTMs, so not by laser altimeter. And but they are available only in some areas of Mercury. We have only just 4 quadrangles available with these kind of DTMs. These DTMs offer complete features. You can are more complete. I mean, you can understand more completely the morphology of Mercury. However, if you want to have a precise measurement of the height, you should refer to MLA DTMs. Sorry. Okay, so MLA DTM, unfortunately, cover just the northern region of Mercury, because MLA tracks were very, let's say, narrow here in the northern region of Mercury, why it was not possible to have an interpolation of MLA tracks in the southern regions. Where the MLA tracks are more spaced, you don't have the same completeness that stereo DTM offers. However, the measurements are more precise because these are precise laser spots on the surface. So let's go back to the presentation. And so now that you have an overview of the messenger datasets, let's see how we can use these datasets to have a final product like this one, a geological map, planetary geological map. Several geological maps were produced for Mercury, starting from the 70s, when Mariner 10 provided the first images of Mercury, covering 40% of the planet. By the time Trask and Guest 1975 provided a geological map exploiting Mariner 10 data. Then the Mariner 10 team also produced quadrangle maps at 1 to 5 million scale that here you can see in a merged version that cover still 40% of the planet. With a messenger mission, the entire planet was covered by MDLS datasets, so it was possible the compilation of a global geological map. This geological map is a 1 to 15 million scale geological map, so a slight lower resolution than the past Mariner 10 maps. So in view of the Bepi-Colombo mission, we are also working on geological maps of Mercury by following the scales that are more similar to the Mariner 10 maps, and we will see it later. But how can we interpret Mercury's surface? So we all know that impact craters, let's say, produce an aging process on the surface and change the terrain appearance in time. So on airless bodies in general, and you may have seen it on the moon, you can say that a terrain is young when it's smooth, and it's old when it's very, very rough and hit by craters. For Earth geologists, it's the other way around. On Earth, we can say a young terrain is actually a terrain where we have sharp mountains, sharp valleys, while it becomes mature, while the valleys excavate, while the rivers excavate the valleys, and we can define that the terrain is old when it's completely plain and eroded by rivers and water. So this is an opposite way of judging the terrain age on planetary bodies. So by following this principle on Mercury, we have three main kinds of terrains. The most famous one are smooth plains and intercrater plains, which are one the opposite of the other. I just like to remind you that all these terrains have volcanic origins. They are all generated by lava flows. But smooth plains are very, very recent lava flows. And with recent, I mean maximum 3.5 gigayears ago. We have no evidence of younger volcanic flows on Mercury than 3.5 gigayears. Intercrater plains are volcanic plains that have placed much before, around 4.0, 4.1 gigayears ago. Intermediate plains, were originally called intermediate smooth plains, are sometimes often more similar to smooth plains than to intercrater plains, but are often cut by important structures such as lobate scarps or very high wrinkle ridges. So they are not so tranquil as a smooth plain is. And you also find larger craters overlapping intermediate plains. And there is no such intensity of large craters on smooth plains. So morphologically, they are more similar to smooth plains, but from an aging point of view, they are more similar to intercrater plains. This is a very difficult terrain to detect on Mercury, but there are some. However, when we look at the color images, especially the enhanced color images, what happens is that we do not have a direct correlation between intercrater plains and blue plains, for example, or smooth plains and yellow plains, for example. Smooth plains can be both yellow or brown or orange. Intercrater plains are often blue, but can be also brownish, sometimes orange. So there is no direct correlation between morphology and colors. And another problem is that the detail we have for morphology is not present for colors, because for morphology we have 166 meters per pixel base maps, while for the colors we have 665 meters per pixel base maps. So they are not so comparable with each other. So this is a problem when mapping Mercury. There is always a dilemma on how to choose the right units. The same thing happens for craters. So, for example, we can classify craters judging their morphology. We can say that this crater, for example, is younger than this crater, because this crater, of course, is subdued by the ejecta of this crater. And this crater here is probably younger than this crater because its ejecta blanket is over this crater, but at the same time is older than this crater because the morphology is a bit rougher. So we can assess a relative age of craters and select their units based on their morphology and on the topography. But if we look again at the colors, another story comes out. From the morphology, for example, we can see that this crater is much younger than this one or this one, because the floor is smoother, the rim is sharper, we can see a very textured ejecta. However, when we look at the colors, we can see that all these three craters exude the blue material. So what should we do? Should we map the morphology to say that this is younger than this and this, or should we map the terrains to say, okay, we have the blue unit here and the yellow unit here. So this is always a matter of scale. And before starting a geological map, we have to select, okay, what do I want to tell the people? Do I want to tell the relative age of events via morphostratigraphic method, or do I want to tell the story of units that shaped Mercury in time via a geostratigraphic method? This is always a dilemma. For now, I will show you what we usually do on Mercury. We mainly usually follow a morphostratigraphic method because the highest resolution is offered by the monochrome base maps. So we detect the units by checking the morphology of the terrains and also classify craters based on their morphology. In our case, for the European mapping project of Mercury, we mainly use globally a 3 classification stage system for crater degradation, but it also exists a 5 degradation class system, which can be used with craters, and you can find details on the Kinchik et al. 2020 paper, where each degradation stage is usually associated to a Mercury period: Kuiperian, Manchurian, Calorian, Tolstoyan, and pre-Tolstoyan. So, of course, this is always a relative aging method. In our mapping projects that we are doing in Europe to prepare us for the Bepicolombo mission, we decided to follow a mapping style more similar to the Mariner 10 maps that were done in the 70s. And we map Mercury with the quadrangle geological map series at 1 to 3 million scale, which is a 1 to 3 million scale because this is the best scale that is achievable by using the available base maps. So this is still ongoing work. As some quadrangles are already published. For example, the northern mid-latitude quadrangles are all published. One of the latest quadrangles published is H14, and then we have published recently, I think it's online since yesterday, the H06 Kuiper quadrangle. So you can find it online, also this quadrangle now. So yeah, so basically when we do the mapping of Mercury, we mainly rely on a morphostratigraphic method. This is an example of a completed map of Mercury where the units are selected with a morphostratigraphic method. And we provide, of course, a legend, a variable scale bar that takes into account the change of the projection scale throughout the latitudes, and several other information that closely follow USGS standards for USGS maps. And of course, when we do quadrangle mapping, we also want to achieve a global product by merging the quadrangles. So if a person works on this quadrangle and another person works on this quadrangle, how can we merge the boundaries? I mean, after all, a geological map is an interpretation procedure. So I can interpret a unit differently from how you interpret the unit. If you put 10 different geologists mapping the same area, you will get 10 different maps. So how can we achieve something like this, a precise boundary that matches one quadrangle to the other? of course, we have to discuss. As you can see from here, in this case, the contacts were pretty different. And also the units were different. For example, the author on the right, that was myself, decided that these were intermediate planes, and the author on the left decided that these were intercrater planes. So after a discussion, we finally reached an agreement on how to change the contacts and classify craters and units. So this is just to tell you that when mapping a planet via photo interpretation, it is always important to discuss what you do with other mappers. And of course, the morphostratigraphic method can lead us to achieve a stratigraphic column of a history of the quadrangle. For example, here in this quadrangle, by counting the craters on the main units, we can assess their relative age by seeing that, for example, intercrater planes are indeed the oldest unit, and what the mapper chose, there were intermediate planes via morphostratigraphic approach were indeed a younger unit that intercrater planes, and spoof planes were the youngest unit. So the morphostratigraphic method is not just saying, okay, this is smooth, this is rough. It's a way to get stratigraphic history, the history of the area of your mapping. And of course, we can do geological mapping even higher in detail. For example, this is an example on how we map hollows and vents inside a crater. This crater is pretty small, so in the geological mapping campaign it would appear just as a yellow unit without any other differentiation. But if the crater is interesting for answering some science questions, for example, how do hollows form, how do vents form? So you may use geological mapping to get a high detail history of the area. And to conclude this and to answer the first question, how can we solve the dilemma of doing a morphostratigraphic map or a geostratigraphic map? Well, in some cases, some authors decided to associate the two maps. I mean, in some cases, it might be useful to map the same area twice with two different methods to compare what is a geomorphologic unit via photo interpretation of monochrome images to a geostratigraphic map showing the interpretation of colors. And in one of the latest papers available, I think from Wright et al. 2020 or 21, I can't remember, the morphostratigraphic units can be subdivided into subunits based on colors. So this is a decision that has to be taken in advance, depending on the questions, science questions, and science rationale behind your map. So this is everything for the geological mapping side, and I'll be happy to take your questions.
Thank you very much, Valentina. We do have a question already. Meanwhile, if you have other questions, please drop them in the chat because we have a few minutes. So the first question is, why have you decided to use 3 degradation states in Europe instead of 5?
Okay, this because when we started mapping the quadrangles of Mercury, the 5 degradation system by Kinzik et al. 2020 wasn't already released. It was available a 5 degradation classification system by the Mariner 10 team that, however, defined that classification systems on craters confined to the Caloris area in the 40% of Mercury that was covered by Mariner 10. So the 5 degradation system that was available at the time wasn't always easy to use with messenger images that were at a higher detail, and sometimes the more classes you choose, the more difficult to match is the stratigraphic interpretation, because it may happen that a very young crater that is next to another young crater, and it may happen that the other young crater subdues and degrades the morphology of the other crater. And so you may end up classifying that with a lower class, while actually those two craters have the same class. So by reducing the crater classes, degradation classes, we reduce the bias in judging the relative age of the craters. So this is what's just our choice, to reduce the bias in understanding the relative ages of craters at the scale we were mapping at. So the 5 degradation class system, for example, was initially based on craters larger than 40 kilometers. So it is very reliable on craters larger than 40 kilometers and less reliable for craters smaller than 40 kilometers. In these maps, we are mapping craters larger than 20 kilometers. So a 3 degradation class systems help us reducing this bias. That's it. But in any case, our mappers are now applying both systems. So in the latest maps, you can see both the 3 classification system and the 5 classification systems together.
Okay, thank you. We have other questions. Are the modifications you made when merging quadrangles retroactively applied to individual ones?
Yes, I mean, once we see that there are some differences in the boundary, we change both maps. However, these changes will be released as final only once we have all the merged quadrangles. In the first place, quadrangles are released and published with the mapper's own interpretation. Then we discuss and merge the boundaries and change both the maps that confine to bound with each other. So yes, of course, there will be a version 2 of our maps that will be changed with respect to the published maps. I don't know if this answers your question.
Yeah, I think so. For the mapping exercise of today, will you tell us which method to use? Could you please provide us with a reference stratigraphic scheme to follow? Because yesterday with the moon, I was quite lost not being used to that.
For those people who are doing the Mercury practical, we will show our presentation introducing you to the mapping area, where we will explain you how to map the features and the units. Of course, we will use a morphostratigraphic method.